All right, let's learn some more techniques for evaluating limits when we can't use limit laws and can't use direct substitution. Without further ado, let's jump right in it. Example 4, evaluate some more limits. We'll do 2 more limits today, and that'll fill in technique 3 and technique 4. Part A is going to be the limit as x approaches 1, get ready for this one, of 1 divided by x plus 1 minus 1/2, I had to check my notes, divided by x minus 1. So direct substitution is not going to work if we plug in x equals 1. And again, this really is a rational function and another rational function. So this is a rational function. Direct substitution does apply here. It might have to do it twice for direct substitution because we do have 2 different rational functions, one kind of embedded in the other one. But we can't use it anyway because it causes us to divide by 0, and we can never use a limit law if it causes us to divide by 0. So this is a complex fraction. We're just going to simplify the complex fraction. Okay. There are 2 ways of simplifying complex fractions. The way that I recommend is by multiplying the numerator and the denominator by the LCD. LCD is least common denominator. So we look at all of the denominators. 1 denominator, 2 denominator. If there were a denominator here, we'd also consider that. But there is no denominator in the denominator. So when we look at the LCD to multiply, we only look at the denominators of the little fractions, if that makes any sense. The LCD here is going to be 2 times x plus 1. And what we do on the top, we have to do on the bottom. So we're going to multiply this out. We're going to multiply this out. That's how we're going to simplify this complex fraction. So it's going to require just distribution, and the bottom's going to be a little easier. So this is going to equal the limit as x approaches. And again, this is true everywhere. These limits are only equal if x is not -1. If x is -1, by the way, then this is not true. We're multiplying by 0 over 0 if x is -1. But we're only caring about numbers very close to +1. So x equaling -1 is not a concern of ours. So that's why these limits are indeed equal. So if we multiply this out, this times this first, it's going to be 2 times x plus 1. And we still have that x plus 1 in the denominator from before. Multiply these 2 pieces. That's going to be 2 times x plus 1 divided by the 2 from before. And on the bottom, we're going to multiply these 2 pieces. Let's keep it factored. To learn our lesson from that last video. 2 times x plus 1 from before. No, times x minus 1 from before. All right. It's one of the advantages to me solving problems that I haven't seen in a long time, because I kind of show you lessons to learn, mistakes to make from that previous video. Let's keep it factored for now. All right. So again, as long as x is not equal to -1, we can cancel these no problem. How does this simplify? And again, to be truly precise, that we can multiply, we can do this step since x is nowhere near -1. If x is -1, we're dividing by 0. All right, so again, we can cancel. The reason we can cancel is x is not equal to +1 either. It's very close to +1, but it's never going to equal +1 for this limit. This is equal to the limit as x approaches +1. This first numerator just simplifies to 2. Minus the second one is x plus 1. And the bottom is 2 times x plus 1 times x minus 1. Do not, I repeat, do not under any circumstances do this. You do this, you're going to have a very upset math teacher. We can only cancel in fractions if there are common factors. So we have to keep simplifying the numerator first. All right, so this is going to equal, let's go on to the next page. Oops. This is going to equal the limit as x approaches 1 of 2 minus x minus 1. Just distribute. And let's simplify that numerator a little bit more. Limit as x goes to 1. This becomes 1 minus x. Huh. That's unfortunate. It would have been really nice if we had something to cancel. It'd be really nice if we had a common factor. We still can't use direct substitution. We'll still divide by 0. I wish we could have canceled. Oh, well, let's give up and go home. No. We're very close. This on the top is a plus 1 minus x. This is a plus x and a minus 1. These are opposites of each other. Let's factor something from the numerator. Specifically, what happens if I factor a negative from the numerator? Factors like this. If I take out a negative, well, this is negative x, good. And positive 1. Positive 1, that's good. So we can factor out a negative from the numerator, and then all of our wildest dreams come true. Mathematically, anyway. Again, we can cancel this. The reason we can cancel is because x is not actually equal to 1 here. X is really close to 1, but never equal. And now we get that this is the limit as x approaches 1 of negative 1 divided by 2 times x plus 1. Great. Direct substitution is going to swing in to save the day. This is a rational function. The limit of a rational function is the function value at that point. So this is going to equal negative 1 divided by 4. Like so. All right, we can just plug in 1 because it's a rational function. Because rational function and denominator is not 0. Hooray. The problem is done. We have one more problem for you. Well, I haven't been checking our work recently. Let's check our work here. This is a complex fraction. It's 1 divided by x plus 1 minus 1/2, all divided by x minus 1. No j. All right, and we're curious about this limit as x approaches negative 1. So as x approaches negative 1, wait a minute, I must have typed this in incorrectly. 1 over x plus 1 minus 1/2. Oh, wait, all right, we're curious about the limit as x goes to 1, not negative 1. Because as x goes to negative 1, this limit doesn't exist. As x approaches negative 1, this shoots off to positive infinity on the left and negative infinity on the right. But as x gets close to positive 1, look at these x values. These x values are getting really close to positive 1. What's happening to the y values? Getting to about negative 0.26. Okay, closer to negative 0.25. It's undefined at the point, but all we care about is what's happening really close to that point. Negative 1/4. Was that our answer? Okay, good. It was our answer. All right. Whew. As the limit as x approaches positive 1 is that negative 1/4. Just like we had. Let's do one more. One more of these slightly complicated, messier versions. And again, if you want to go back and fill in step 3, step 3 is going to be simplify complex fractions. Or method 3, technique 3, however you want to label it. So it's really similar to steps 1 and 2. These are all basically just saying, if it doesn't work, simplify and try simplifying tricks. These are really more of simplifying tricks than any specific limit methods. All right, this last one's another good algebra problem. This whole section's algebra. The limit as x approaches 0 of 1 over x plus 5 over x times x minus 5. So limit laws don't apply here. Why do limit laws don't apply? Well, hold on. Let's pull up those limit laws. Jason, what are you talking about? Oh, I pulled up the wrong limit laws. Pull up the different limit laws, Jason. Tab through your 50 windows. So the limit laws say that, all right, in order to use the sum law for limits, functions have to be defined and the limits have to exist and be real numbers. We can't just split this up into the limit of the first and the limit of the second, because look at the limit of the first. The first one doesn't have a limit. 1 over x, as x approaches 0, that's not defined. It goes to positive infinity from the right and negative infinity from the left. So we can't use limit laws to look at each of these individually. We have to look at them combined. So what are we going to do? We're going to use more algebra. Simplify. All of these techniques are just simplify. Again, we can't use limit laws because that first piece, and the second piece for that matter, doesn't exist. I'm not gonna write why. You can write down why if you'd like from my verbal explanation. So let's simplify. The limit as x approaches 0. How do we simplify this? We need a common denominator. So this first piece, what is missing from this first piece? An x minus 5 on the denominator. And the second piece, right? The second piece is actually already done. The second piece isn't missing anything, which is kind of nice. So to get a common denominator, all we have to do is multiply a little bit on that first piece. And again, this is only valid as long as x is not equal to 5. This is only true as long as x is not 5. So this is going to be the limit as x approaches 0 of x minus 5 divided by x times x minus 5 plus 5 divided by x times x minus 5. Great. We have common denominators. If we have common denominators for a fraction, we can add or subtract their numerators together. The denominator does not change, but we do add the numerators together, which is nice because subtract 5 and plus 5, those cancel out. This becomes the limit as x approaches 0 of x divided by x times x minus 5. Ooh, these have a common factor. As long as x is not equal to 0, these will cancel. And x is getting really close to 0, but x isn't actually 0 in this limit. The limit is all about getting really, really close, but not touching. All right, so let's just kind of go up here to finish. It's really quick. So this is the limit as x approaches 0 of 1 over x minus 5. And now this is a rational function. We can use direct substitution and get 1 divided by 0 minus 5, or just negative a fifth. And we could check our answer graphically as well and say, oh yeah, that does look like the function's getting close to negative 0.2, negative a fifth. So that's the last method. I don't really have a great way of saying this, but just simplify. Maybe however you want to say this. Maybe combine fractions. Other ways of just simplifying. Things to look for. So these are the 4 things to look for when direct substitution. Limit laws or direct substitution doesn't work. All right, let me know if you have any questions and enjoy some mathematics for me. I also enjoy mathematics. That's why I do this. I wouldn't be doing this if I didn't like it. All right, bye-bye.